Hello friends, today I am going to talk about Zeeman effect and LS and splitting of spectral lines of atom in the presence of constant magnetic field is Zeeman effect. It is of two types, normal Zeeman effect and anomalous Zeeman effect. What is normal Zeeman effect? Spectral lines show three components when viewed along transverse direction to the magnetic field. Central component has original frequency nu naught, but outer components have frequencies nu naught plus minus mu b by h. When viewed along the direction of magnetic field, central component is absent, but outer components nu naught plus minus mu b by h are present. Here mu b is Bohr magneton. Normal Zeeman effect is a simple pattern of spectral lines. When electron spin is neglected and B field is strong such that minus mu dot B interaction is much more than spin orbit interaction, then we have normal Zeeman effect. I will talk later what exactly is spin orbit interaction. Polarization of spectral lines viewed transverse to B, nu naught component linearly polarized along B direction, while other components are linearly polarized perpendicular to B. Viewed along B, outer components show circular polarization in opposite directions, one clockwise and the other anti-clockwise. And by polarization, what we mean is where in which directions the electric field is oscillating. Anomalous Zeeman effect. In anomalous Zeeman effect, number of component is more than 3 and the pattern is more complicated compared to normal Zeeman effect. Here spin of electron is not neglected and B field is weak such that the strength of spin orbit interaction is much more than minus mu dot B interaction. So, you see it is just reverse of what was there in the normal Zeeman effect. Here spin orbit interaction is more compared to minus mu dot. Now, what is spin orbit interaction? In the rest frame of electron, it is the nucleus which is revolving and produces an internal magnetic field B internal proportional to L vector at the site of electron. Interaction energy of this field with magnetic moment mu s of electron is minus mu s dot B interaction. Now, mu s vector is proportional to spin vector. So, we have spin orbit interaction proportional to L dot s. HSO is the spin orbit interaction Hamiltonian. So, HSO is Fr times L dot s, where Fr is some function which depends only on R. It has no angular dependence. Now, we can have a quick derivation of a spectral line splitting in normal Zeeman effect. Hamiltonian for an electron in an atom placed in magnetic field is H is equal to p square by 2m plus Vc plus HSO plus Hm. The first term p square by 2m is kinetic energy, Vcr is average potential energy due to nucleus and other electron cloud. It is assumed to be central. Now, you must mark that Vcr is different from Coulomb potential. Coulomb potential is central, but here Vcr is not necessarily central. then HSO is spin orbit interaction, it is Fr L dot S as I told you, and then HM is the interaction of mu with the magnetic field, and the mu has now two sources, one from orbital angular momentum and other from spin angular momentum, and this you can see that minus mu b L plus 2s dot b, and L plus s is now total angular momentum j. So, you write H m as minus mu b j plus s dot b. This is the point to be noted, that the interaction energy of magnetic moment with external B field is now mu b times j plus s dot b, where mu b is again Bohr magneton. In normal Zeeman effect, magnetic field is assumed to be strong and spin is neglected. For B along z axis, we have H is equal to H naught minus mu b b by H bar L z, and now psi n L m is a state of electron which is now 2L plus 1 fold degenerate when B is equal to 0. The degenerate means there are many states corresponding to the same energy. Now, this degeneracy is lifted when B is not equal to 0, and the possible energies of electrons are E n L m, that means E depend on n, L and m, it is E n L naught, that is energy in the absence of B, minus mu b b times m. So, the modification is minus mu b b m, and it depends on m quantum number. Now, for various n prime, L prime, m prime to n L m transitions, selection rules delta L is equal to plus minus 1, delta m is equal to 0, plus minus 1 are obeyed. With these rules, triplet of normal Zeeman effect are observed, and nu 0, nu is equal to nu plus nu 0 plus minus mu b by h, where delta E n is h nu naught. What you see here is the normal Zeeman effect, and what you see here is L plus 1, L is equal to 1 and L is equal to 2 levels. L is equal to 2 level is split in 5 parts, 1 in 3 parts, and various transitions have been shown, and with the selection rules in mind, what you can see is that just 3 lines are possible, nu naught plus minus E b by 4 pi m. Now, we go over to energy level splitting in anomalous Zeeman effect. In anomalous Zeeman effect, magnetic field is assumed to be weak and spin orbit interaction is assumed to be strong, unlike normal Zeeman effect where spin is neglected. Spin plays an important role here. So, HSO is much more than HM. H is again p square by 2m plus VCR plus HSO plus HM, and here we have separated the HM part from the rest. So, H is equal to H0 plus HM, where HM is the interaction of magnetic moment with the field, and HM we have already shown, that is minus mu b b by h bar Jz plus Sz, and it is small in magnitude. Now, psi n j L s is a state when B is equal to 0, it is 2j plus 1 fold degenerate, and this degeneracy is lifted in the presence of magnetic field. Change in energy due to HM interaction is delta E is equal to minus mu b by h bar J z average plus S z average, where angular brackets denote average over the state psi n j L s. If we want to find out how much the energy has shifted, we must calculate Jz average and Sz average. Now, Jz is mh bar because it is quantized as we have already seen, and Sz average by some rules of quantum mechanics, which I would not elaborate here, is J dot S Jz by J square. Jz is known again, and J dot S can be computed from L is equal to J minus S, and the values of L square, J square, S square are known as L into L plus 1, J into J plus 1, S into S plus 1, and we define G j as you see on the slide, and this leads to delta E is equal to minus mu B B G j m. This is the shift in the energy, and as you can see, this shift depends on quantum numbers j, s and L and m. Pattern of anomalous Zeeman spectral lines is not simple. Splitting of energy levels 2p half and 1s half in the presence of magnetic field is shown. Now, again we have the selection rules coming into play. N prime, L prime, J prime, M prime, 2 N L J M transitions are subject to selection rules. Delta J is equal to 0, delta J is equal to 0 plus minus 1, and delta M is equal to plus minus 1. Further, J is equal to 0 to J is equal to 0 transition is not allowed. So, under these selection rules, we have the splitting and various transitions. What you see in the slide is anomalous Zeeman effect, and you see 4 lines, because the levels 2p half and 1s half have split, and these 4 transitions only take place because of the selection rules. So, you have now 4 lines instead of just 1 line. So, this is what is anomalous Zeeman effect. Now, we talk of LS and JJ coupling in 2 electron atom. Here we have one modification from 1 electron atom. From 1 you have moved to 2 electron. So, when there are 2 electrons, then you write the energy term, that is Hamiltonian. So, you have first one term corresponding to 1 electron, which is kinetic plus potential. Then for the second, again kinetic plus potential. Then you include spin orbit interaction, which is HSO. It is xi1 L1 dot S1 plus xi2 L2 dot S2. Then you have HER. This term was not present before, because it is the electron mutual Coulomb repulsion. It is E square upon 4 pi epsilon 0 1 upon R12. It depends on the separation between 2 electrons. It is the electron repulsion energy, and here 1 and 2 refers to 2 electrons. When I say 1, it is electron number 1, when I say 2, it is electron number 2. So, you write the Hamiltonian for 2 electron atom in this way. Now, what is there in LS coupling scheme? In LS coupling scheme, electron mutual repulsion energy is much more than spin orbit interaction energy, which means HER is much more than HSO. So, the larger part is H0, that is H is equal to H0 plus HSO, and H0 contains kinetic and potential of 1 and 2, and HER is the electron repulsion energy. So, HSO is a small contribution over and above H0. In the JJ coupling scheme, spin orbit interaction is assumed is much more than mutual Coulomb repulsion interaction energy, and HSO is much more than HER. So, now you have H is equal to H0 plus HER, that means the larger thing is H0 and HER is small correction over and above H0. and H0 contains now kinetic and potential of 1 and 2 plus HSO, that is the spin orbit interaction, because the larger part is now spin orbit and the small correction is HER. Now, what are the quantum numbers in LS coupling scheme? We are considering two electron system. So, total orbital angular momentum L is sum of two momenta L1 and L2. So, L vector is L1 vector plus L2 vector. L square and Lz are commuting operators and their eigenvalues are L into L plus 1 h bar square and ML h bar, and capital L again takes the values 0, 1, 2, 3 etc., and these states are labeled by S, P, D, F. Now, you mark the difference. Here we are denoting by capital L, earlier we denoted by small l, because now we have two electron system and earlier we denoted states by small s, small p, small d. Here we have capital S, capital P, capital D. So, for a given capital L, ML takes all values 2L plus 1 values from minus L to plus L with the interval of unity as we did before. When values of L1 and L2 for 2 electrons are given, L for system of 2 electrons can take all values from minus L1 by 2 mod to L1 plus L2, L1 plus L2 with the interval of unity. This is how you obtain total angular momentum given the two values L1 and L2. For example, for 2p electrons, L1 is equal to 1, L2 is equal to 1. So, possible L values are 0, 1 and 2. Similar considerations hold for spin states. For total spin of 2 electron system is S is equal to S1 plus S2. Now, again S square and Sz are commuting operators and their eigenvalues S into S plus 1 h bar square and Ms characterize the spin states of system of 2 electrons. Possible S values are S1 minus S2 mod to S1 plus S2 with the interval of unity. For a given S, Ms take all values from minus S2 plus S with interval of unity. For example, for 2 electrons, S1 is half, S2 is half. So, the possible S values are 0 and 1 only, and possible Ms values for S is equal to 1 are minus 1, 0 and 1. Total angular momentum J is L plus S, and quantum numbers associated with J vector are J and Mj. Possible values of J square are J into J plus 1 h bar square, and those of Mj for a given J are minus J plus 1, J minus 1 J. Now, given L and S, possible J values are from modulus of L minus S to L plus S with the interval of unity. Thus, quantum numbers in LS coupling scheme are capital L, ML, S, MS, J and Mj. For a single electron system, we were using small letters, and for a system of 2 electrons, we are using capital letters. This is the difference we are using. In terms of vector model, vectors L1 and L2 precess about their resultant L. Vectors S1 and S2 precess about their resultant S vector. Both L and S precess about J vector. In LS coupling scheme, precession of individual L about capital L and precession of individual S about capital S vector are faster compared to precession of L vector and S vector about J. This is a important point, that which precession is faster and which precession is slower. Here you see that these two vectors L1 and L2 and each L vector is suffering a torque L1 dot L2 due to another L vector. So, neither L1 is constant nor L2 is constant, but still you can define a vector L is equal to L1 plus L2, which is sensibly constant. So, here you have the vector coupling of L1 and L2. Similarly, you have vector coupling of S1 and S2. L1 and L2 then precess around capital L, S1 and S2 precess around capital S. Now, you talk of another scheme which is quantum numbers, which is JJ coupling scheme, and now we talk of what are the quantum numbers in JJ coupling scheme. Due to strong spin orbit coupling, L and S couple to give a J for each electron. So, for each electron you have J1 and J2. J1 is L1 plus S1, J2 is equal to L2 plus S2. J1 and J2 couple to give the total angular momentum J is equal to J1 plus J2. Possible values of J1 are from minus L1 S1 mod to L1 plus S1 with interval of unity, and similar argument holds for J2. Possible values of J square are J into J plus 1 H bar square, and J can take all values from J1 minus J2 mod to J1 plus J2 with interval of unity. So, you appreciate the difference. Earlier you had L's L1 and L2 combining to give L, S1 plus S2 combining to give S, and then L plus S combined to give J. Here you have L1 and S1 combined to give J1, L2 and S2 combined to give J2, and then J1 plus J2 again combined to give capital J. So, this is the difference between two types of coupling. Possible values of Mj for a given J are 2J plus 1 values minus J2 plus J spaced by unity. Then quantum numbers J1, J2, J, Mj are useful in describing the state of two electrons in JJ coupling scheme. In terms of vector model of atom, precession of L1 and S1 about J1 and precession of L2 and S2 about J2 are faster than precession of J1 and J2 about J. L1 and S1 are combining to give J1, L2 and S2 are combining to give J2, and then again J1 and J2 are combining to give capital J, and the capital J is space quantized in the sense that its projection on z axis are Mj h bar, and Mj h bar cannot take all possible values. For a given J, it will take the values minus J to plus J h bar is spaced by unity. Now, LS coupling is more frequent and it is applicable to many light atoms. Both LS and JJ coupling are two types of limiting cases. Intermediate couplings are difficult to handle mathematically. Basically, what we have done is that there are some extra terms over and above the usual kinetic and potential terms. We have identified those terms. So, these terms are HSO, that is spin orbit interaction, and then the other term was HER, that is the interaction term corresponding to repulsion energy between two electrons. We take two extreme cases. In one extreme case, we have LS coupling. In LS coupling, what we saw was that HER term was large and HSO term was small. In the JJ coupling, we took the another limit where LS coupling was large and HER was small. But then we must appreciate the fact that in real life, it is not always the case. We do not work on the extremes always. We must have some intermediate situations. But unfortunately, mathematically it is difficult to handle intermediate situations. But for many light atoms, LS coupling is good enough and it explains many observed results. So, friends, we have seen Zeeman effect, both normal and anomalous. In the anomalous Zeeman effect, spin was considered, but it was neglected in the normal Zeeman effect, and overall we saw how the spectral lines get split because of the external magnetic field.